Hi, my name is Jeff Coronado from JCSE, and this is a session in Bridging the Gap. The title of this particular session is Truss Modeling -1. This is this is somewhat associated with those of you that are in-house. This is somewhat associated with the W Truss 1 sequence. So if you are in-house, you can follow along. If you're not, I'm sure you'll learn, or hopefully you'll learn a few things. Um, in particular, what we want to address is what is meant by the Z rotation, in the computer model of a truss. So the Z rotation is one of those concepts that's somewhat straightforward to understand, um, somewhat simple, and yet it isn't. Yet sometimes it plagues people. It gives some people a little bit of trouble. And if nothing else, it's such a small issue when you're doing computer modeling that it can be so easily overlooked. And that's where one of the axioms or the axiom of junk in, junk out comes in, right? It's something that can be a small mistake in your computer model, but if you're not aware of it, if you miss it, you can be getting some pretty erroneous results, and you just overlook it. So let's try to see if we can get squared away on Z rotation. Let's clear the screen here and scroll down here a little bit. So as I mentioned, this image here is taken from W Trust One, for those of you that are in-house, and you can follow along. Let me see if I can zoom in a little bit here, um, because I think we want to explore some of these things. Okay. Um, as we have seen, the truss is an assembly of discrete elements that, once assembled, act as a beam. I believe that was covered in another Bridging the Gap session. But essentially, that is correct, right? Um, so first, let's focus on the members that compose the truss, the assembly of the truss. All right, so we have the top chord. Um, and the top chord is this element here. So let me see if I can go there and there. Okay, so this is the top chord. So how do we think of the top chord in a truss? Well, let's see. The top chord is what? It's the topmost element. You can see that there is nothing above the top chord, right? Again, so this is our top chord. I'll use a highlighter here. This is our top chord. There is no member above the top chord in our truss. Um, what else? It is essentially horizontal, and you can see that I'm taking, even in this example, we're taking a little bit of liberty in saying that it's essentially horizontal because this does have a pitch. It is somewhat diagonalizing, but by and large, there is more horizontal to this than there is vertical, right? So it is essentially in the horizontal plane, even though it has a pitch. Um, and let's see, and it essentially extends from one end to the other. The top chord will extend from one end to the other. By extension, the bottom chord, similarly speaking, the bottom chord of the truss means that there are no members of the truss that are below the bottom chord. It essentially spans from one end to the other, and it is essentially horizontal. Now, that's not to say that there aren't some deviations from that concept of horizontal. So for instance, the top chord can be perfectly horizontal. We can have a truss that does maybe something like this. Uh, see here. Hmm. Uh, uh, what the heck? We can do something like that, right? All right, so we could have a truss. Let's see, how do I close this out? I think this would be stable. So we can have a truss that's configured like this, where the top chord is completely horizontal. We can have a truss where, let's say, none of the chords really are horizontal. Say that's our top chord, and we could have a bottom chord that does something like this. And that would still be a truss. Could be doing something like this in terms of the web members, which we will get into in a minute. But essentially, okay, essentially, if you work with me anyway, the top chord and the bottom chord are essentially horizontal. So essentially horizontal, going from one end of the truss to the other. And again, with the top chord, there are no members above it, and the bottom chord, there's no members below it. Okay? So those are the chords, what we refer to as the chords of a truss. Um, So the top chord is the uppermost, essentially horizontal, extends from one end, understanding the bottom chord, bottommost, essential. Okay, the web elements. All right, so the web elements, members of the truss other than the chords, they can be diagonally oriented, and then we refer to them as diagonals or vertically oriented, and we refer to those as verticals. Okay, so the diagonal members or the webs are sorry. So that's a web. This is a web, right? Or diagonals of the truss. The internal members, other than the top chord and bottom chord, are the web members of the truss. They can be diagonal. Sometimes we will place them vertically. As again, as this was covered in another session of Bridging the Gap, those members are selected at locations that are strategic um, to be able to carry the loads, the internal loads that the truss needs to carry. One of the things, and we don't want to get into this in this session, that's not what this session is for, but one of the things that you may be noticing is that these internal members, these webs, basically create a lot of triangular shapes, right? See that there's a triangle here, there is a triangle here. We basically create a lot of internal triangles with the web members, and the reason for that is because we meaning engineering, humanity, if you will, has discovered that triangular shapes are very stable. So that's one of the reasons why that one of the driving forces between the location or of the location of where web members are located within a truss. Okay, so those are the internal members of a truss, the webs, the diagonals, verticals. Let me see if I can clear this and we can keep going. So we got the web elements. Okay, connectors. Connectors occur at the ends of the web elements and the chords. Okay, so if we go back to our picture, so connectors occur at the end of web members and chords. Okay. So that means that hoping you can see that red shaded circle. So here is the end of this member of the top chord, right? So we would have connectors at each end of that member of the top chord. Here is a second member of the top chord. Oh, and yes, by the way, in case you're wondering, yes, I am ignoring this little I am ignoring this little extension of the top chord. Okay. So for simplification purposes, we ignore that that's there. We just basically say that the top chord is supported at this wall. So it goes from the wall support to where it meets the other top chord, and likewise with this top chord member, goes from the wall that supports it to where it meets the other top chord. Okay, so we have a connection at each end of the top chord member, and we've kind of shaded that in with red circles. And likewise, oh, I'm sorry. Let's see here. And so for the web members, let's see, we would have a connection at this end as well as this end for that web member at each end of this web member, at each end of this web member. So at each end of the web members, we have a connection. And then the other one that we have to think about here is the bottom chord. Well, the bottom chord, we would have a connection at this end, but then notice here, notice how there is a splice in the bottom chord. And this sometimes can goof some people up. So here we have a splice in the bottom chord. And why is there a splice there? Well, because the reality is, even though we wish we could make this bottom chord continuous all the way across, and there's no reason from a theoretical point of view to not make it continuous. Um, but the reality is, and again, keep in mind, this is for W truss one. So we're talking about lumber trusses. So for a lumber truss, there is only a so long that a wood member can be, right? That might be 10 feet, might be 20 feet, might depend on the region of construction where this is occurring. But there are practical limitations on how long that member can be. There could be issues with transportation, trucking, right? Think about the last time that you saw a piece of wood, a wood member on a truck, on a flatbed, going down the highway that was 40 feet long, right? Doesn't happen too often. Um, so the reality is that the bottom chord can't just be indefinitely long. So we have to splice it. So here there is a splice. So that becomes the end of the member of this particular member of the bottom chord. Let me see if maybe we can kind of do this in some different colors, different shading. So I'm going to say that the bottom chord is composed of this member in blue and this member in cyan. Right? Together, they're the bottom chord, but they are two different members in this bottom chord. It's not just a continuous piece of lumber. There is a connection, a splice. Therefore, there is a connection here that we need to address. Right here, there is a connection. So that's what we mean by the end of a member. So we have connections at the end of each member, as we showed on the top chord with all of the red filled in circles. And at each end of each of the web members, there is a connection. And the bottom chord likewise has connections at each end, but there's also an intermediate connection at the splice. Okay, hopefully that is clear. Connections occur at the ends of web elements and chords. Connections also occur where there are splices. We covered in this example how there is a connection, a splice that occurs in the bottom chord, right? Notice how there were no splices in the top chord, but that's not to say that they don't occur and don't occur with some frequency. So the reality is it would not be unreasonable to see a splice somewhere in the top chord, somewhere here or here, in which case then the same thing. You have a splice and therefore you would need a connection at this point. Okay, so wherever you have a splice, a physical splice in the member, that has to be modeled as a connection. Um, Okay, where there are connections, there are nodes. Okay, so yes, now we're getting into kind of a little bit of the idiosyncrasies of computer modeling a truss. So for purposes of modeling a truss, um, if we look, let's take a look at this connection right here. No, you know what? Let me skip that one. Let me skip that one. Instead, let me look at this connection. For this purposes, I think this will be an easier one to first use to explain. Okay, so in this connection, um, the reality is we have a top chord going up, a top chord member going down, and then a diagonal web member or two diagonal web members coming down from that connection, right? So we'll use little squiggly lines here to show that we're cutting off these members. We're not showing the full length of the members. So that's what we have in this top connection. Um, this is kind of what we really have, right? But for computer purposes, for modeling purposes, what we actually have is this. So the connection itself is a node. The computer, the model, I'm sorry, the software, the software will treat that connection as its own entity. And we represent that with this rectangle. That's how we represent those connectors. The connection is represented with a solid rectangle. Um, so the connection itself becomes its own entity as far as the software is concerned. So we have members that don't frame into each other, kind of like what happens right here, which is more reality, right? These two are actually butting into each other. Instead, the way the programs will look at it is the member frames into the node, and the node then goes into the next member. Okay. So let me see, before clearing this screen, um, let me see if I covered what we needed to cover on that. So where there are connections, there are nodes. Computer models model the connection as its own entity. We represent that with a square. Okay. Okay. So I think with that, we can, well, you know what? I didn't have to scroll up. Let me clear this screen. And then let's see what the next concept is here. Where there are connections, we represent, in some cases, all members terminate at the node. Okay, that's kind of what we were illustrating in this top connection, right? All members at this node, all members at this node terminate at the node, right? Meaning that if here's our node, and the top chord that comes in from the left, that member ends at the node. Top chord member that comes in from the right also ends at the node. And the two web members end at the node. Okay, so sometimes all members that are framing into a node end at the node. By extension, by extension, there are nodes where that is not the case. Let's look at this one. All right, so in this case, we have we'll have our node because we have a connection, so we have to have a node. But if we have a node, that means that the bottom chord has to frame into the node. The And then, I'm sorry, did I say bottom chord? No, the top chord, right? The top chord has to frame into the node. And then on the right side, likewise, right? Then the member extends out, continues on from the node. And then there's the diagonal web member that frames into the node. So this is what the program is going to see or think of. This is how the program thinks of this connection. Now, let me see if I can scroll down and not lose this image because I want to make sure um, where there are connections, there are nodes. Okay. In some cases, okay, some programs members must be modeled from node to node. Okay. Let me now scroll up because here we there are some differences depending on the program that you may be using. So some programs will think of this member the way this is illustrated. Now, there are programs that will treat this a little bit differently, and I will show you. How do I want to do this? Let me draw the node over here, and then here is the top chord, and here is the web member. Okay, so as an example, let me use light green and dark green. I am going to circle, or I'm going to put a cloud in this. I think this is the light green. So light green, some programs, you can model this connection in this fashion. And Riza 3D is an example of that. So if you are modeling in Riza 3D, you will see that Riza 3D allows you to define a member to be to be a physical member, I believe is the way the program references it. So it's a physical member. So therefore, you would define the member to go from, and I'll stay in green here. It'll go from this point, from this connection all the way to this connection, which represents realistically what that member is doing, right? Because this is a single member. After all, this is a single member that goes from this connection in green to this connection in green. And it goes right through the node because we still need the node there so that we can connect the web member into the top chord. But the program will understand if you define the top chord to be a physical to be a physical member or have physical properties. You'll have to kind of check in Riza when you're actually modeling it. When you're actually modeling the member, it'll give you that option. And it's something like physical. I forget exactly how it's worded now. But if you are using Riza 3D, then you can model this member as a continuous member from this node in green all the way to the other node in green, um, and and then define the web to go from this node here down to the node wherever it ends up, which in this case is down here. Um, So you can do that in some programs. In some programs, you cannot do that. And EnterCalc is an example of that. In EnterCalc, you do have to show this the way I am showing you in dark green. Okay, so this is how you would have to do it in EnterCalc. In EnterCalc, even though the member is continuous, it needs to stop for purposes of the program. The member needs to stop at the node, and then you need to draw a separate member. So it'll be one member extending from this connection to this connection, and then a separate member from this connection to this connection. Even though the reality is it's just one member, but that's how EnterCalc is going to want you to model it as two separate members whereby they each stop at this node, or they are connected through the node. Okay, so hopefully this is clear. See here. So in some cases, one of the members that frames into the node does not terminate at the node. In some programs, members must be modeled from node to node, such as EnterCalc, right? The member must be modeled from node to node. Okay, I'm going to clear the screen here. So again, if you were using Riza 3D to model this top chord, you would say this top chord goes from this node to this node. You define it as a physical as a physical member. You define it as a physical member, and then you can draw a node here at midspan. You can draw a node. You can have a node, define a node at midspan of that member, not at midspan, anywhere along the length of the member, and then and that way you can frame elements, web members into it. With EnterCalc as an example, with EnterCalc, you would have to define one member from this node to the very next node. So in other words, in EnterCalc, you can't bypass a node with a single member. We cannot do a single member from the node down here up to the node up here. We have to do a member that goes from this first node to this node, and then another member, define another member that then goes from this node here to the top node here. Okay? Um, so in some programs, members must be modeled from node to node. That's where then the concept of the Z rotation restraint, which can also be referred to as fixity, comes in. Because now we have to somehow, as you can imagine, we have to somehow alert the program that even though these are two separate members that are framing into I'm sorry, they're not two separate. Well, as far as the computer is concerned, as far as EnterCalc is concerned, as that example, it thinks there are two separate members that frame into this node. But again, we know that they are not two separate members. It's one single piece of lumber that is at this node, right? The top chord is one single member. And the way we do that, the way we alert the program that that is a single member is by using the Z restraint. Okay, so let me clear this. Okay, so now we're getting into Z restraint. Okay, let's spend a little bit of time here discussing um, the Z rotation restraint, which we can also refer to it as fixity, and the opposite of fixity, which is a pinned condition. Okay, so those are the two extremes that we deal with. We will not get into anything in between. All right. So the idea of partial fixity is not something that we deal with in terms of lumber trusses, lumber trusses. Okay. So we deal with the two extremes. It's either fully fixed, either a connection is fully fixed, and if it is not fully fixed, then it's pinned. All right, so what do we mean by pinned? All right, for pin, the easy illustration is to think of the two hands of a watch. All right. So real simplistically, if you have a watch, all right, and you have the hands of the watch, and let's say it's 3 o'clock. All right. Um, okay. So these hands in a watch are free to spin around, correct? Right? This guy can spin around here, and so can this little guy. He can spin around, all as long as they are going around that middle point or the end of the two hands, right? They can spin about this point. So the big can be here, can be here. It can spin all the way around, and likewise the little hand. Screen, the little hand can spin all the way around as long as it's about the end of where the hands occur. All right. That's what we mean by a pin condition. Notice how these two hands can't take off and run, right? They can't be over here. They can't end up over here. They can't end up down here. They are free to rotate as long as it's about this point. But they are free to rotate. And they're free to rotate, and therefore the relative distance between the two of them can also change, right? So for instance, the big hand can end up here with the little hand right here. The big hand can end up down here, and the little hand is up here, right? They're not locked in. The space between them isn't locked in. The only thing that's locked in is that the end of the two hands can't move from this location. That's essentially what we mean by pinned. Okay, so the two hands can rotate with respect to each other. The two hands can rotate with respect to each other, but they cannot displace with respect to each other. No matter what, those two ends need to be connected, right? Whether the big hand is here and the little hand is here, whatever it is, but notice how the fact that the two ends are connected, that doesn't change. That's what cannot change. The angle between them can change. The angle between them can change, but not the fact that they're connected at the end. That can't change. All right, that's what we mean essentially by two members that are pin connected. Now, when we want to think of fixity or z rotation restrained in the z rotation, what we mean by that is now think of our two hands, but think of applying glue. Think of applying glue right here where they meet. All right, if you glue them and then let them sit for a little while, then what happens? They are no longer free to rotate with respect to each other, right? They're locked in at that angle. They're locked in. You might be able to rotate both of them together, right? You might be able to get them to rotate together, but relatively speaking, that angle between them doesn't change. The ends will stay connected. The ends will stay connected as they are here and here and here and here. The ends stay connected, and the angle between the two members doesn't change. So therefore, this is fixity. This is a connection that is fixed. Or another way to say it is it has zero z rotation. They are fully restrained in their z rotation. Okay, so fully restrained, z rotation, fixity, they all mean the same thing. All right, now with that, let's clear this and let's see where that takes us. Um, members that are continuous, all free ends, okay. Members that are continuous through a node are modeled as fixed. Okay, so let's go back to our model. Now, one of the things that you should know is that in lumber, standard practice is that we always model the ends of members, lumber members, as being pinned. Okay, so I'm going to use green. Yeah, I can use green. I'm going to use green. So that means that this top chord at this point, at its end here, is a pin. So that means the Z rotation is free to rotate. Here, the Z rotation is free to rotate. For the top chord on this side, Z rotation, free to rotate. Here, the Z rotation, free to rotate. For this web member, at this end, the Z rotation is free to rotate. No fixity, right? No fixity. In this web member, no fixity. In this web member, no fixity. At the end of all of the members, there is no fixity. The ends of all members are free to rotate. Um, let me, I know that those green circles are a little bit hard to see, but that means that the lines, these members that I'm drawing in green, all of these members have the Z rotation set to free to rotate, meaning they're pinned connections. They are not fixed connections. All of the members in green, that is true. All of the members in green have a pin connection at each end of them. Um, now the bottom chord. Okay, why is the bottom chord a little different? Well, the bottom chord is a little different because remember that the bottom chord had this splice along the middle of its length, right? So that means that what happens, so what happens over here? Well, there we have the end of a member, right? So if we pick another color here, let me use yellow. Can we see yellow? Yeah. Okay. So that's one member of the bottom chord, right? Well, on the left side of that member, that's the end of the bottom chord. That's the end of the wait. Actually, this is not a good example because this one will be pinned on both ends. I'm sorry, this one will be pinned on both ends, right? Okay, we can finish this up. Doesn't hurt. Um, but do I stay in yellow? Yeah, sure, right. Ooh, that's not easy to see. Pick another color here. See if I can go to blue, maybe. Okay, so the left end of that member, that's the end of the member, right? That one is pinned. What happens on the right side of the member? Same thing, right? Same thing. It's the end of a member, pinned by definition, pinned, right? That's the standard of the industry. We always look at the end of wood members as being pinned. So that member is pinned. Um, okay, now let's look at the top chord. Let's look at the top chord because the top chord, remember, if you are modeling in Riza, you are able to treat that top chord as spanning from the support here at the wall all the way up to the apex of the truss as a single member. But if you are modeling in InterCalc, remember we said this had to be treated as two separate members, right? So one member that spans between the node here at the support, and then and it spans to the node where that's created so that you can frame this web member. And then the chord continues from there up to the apex. However, the reality is this is a single piece of lumber. There is no splice there. This is a single piece of lumber, right? So here we would treat that connection differently, or the end of that member differently. So whereas the bottom end of this member is pin, the top end we say is fixed. That's how we let the program know, or that's how we begin to let it know. Let me do the other one. What do you think happens in this member? Well, same thing right here. That end of that member, you would say is fixed. There is zero rotation, zero Z rotation, zero Z rotation at this end of the member, and free to rotate at the other end, at the top end, free to rotate at the top, but zero rotation here. So by making this zero rotation and this zero rotation, that's how, in essence, you have let the program know the reality is this is a single member. That's how you would need to model this in EnterCalc. Okay. Let me clear the screen. Um, That might be it. Think of a fix. All free ends of lumber. Lastly, members that are continuous through a node are modeled as fixed. Lastly, all nodes are to be modeled as having Z rotation restraint. You know what? I don't know that I want to go back and do this, but redo this. But I don't think this is true. Let me make sure. Members that are continuous through a node are modeled as fixed. Yeah, like the top chord that we just did, right? Where we need to have a node to frame the web, but the reality is the member is not discontinuous. There's no splice there. That top chord was continuous through the node. So the way we handle that is by alerting the program that that there is fixity. There is fixity in that member or in those two members at that end. You have Z rotation restraint. Okay, so no fixity means Z rotation restraint at that end. Lastly, all nodes are to be modeled as having Z rotation restraint. No, that's not true, right? We've now covered that. So this statement should not be here. We've seen how in some situations, probably most situations that you encounter, because the connection is pinned at the end of all members, um, then you're going to have mostly pinned conditions, pinned connections. But wherever you have a continuous member going through a node, then you have to interrupt the member at that node, but then you have to apply fixity at the end of the member that frames into that node. Okay. And again, that's only in some programs, such as EnterCalc. Riza works a little bit differently, like we explained. Okay. But I think with that, we are done. Let me see. Let me make sure. Yeah, we are done with this session of bridging the gap. Okay. All right. Real good, guys.